100 done. Let's go to 101. Yeah, forward, not backward. Okay, I'm moving forward. Yes, 101. So what is it? It is having gone through a plank of thickness h. So plank of thickness h. A bullet changes velocity from v0 to v. So this is a bullet. It initially it's v0, and then having gone through it, it changed to v. Right. Find the time of motion of the bullet in the plank, assuming the resistance force to be proportional to the square of velocity. Oh, so the force is proportional to square of velocity. Acceleration is also proportional to square of velocity. So like acceleration is equal to negative, because of course it's retarding. Negative, I don't know, some kind of constant that times v squared. I should do it. Oh, this is v as well. Let's just call this v1, right? So whenever the bullet is in between whatever velocity it has, this will be the thing. And it isn't that hard. Okay, so you just need to figure out first of all, you need to figure out what k is, because without knowing that, how am I going to even do anything? So how do you figure that? Of course, right acceleration is v dv upon dx, and then this will be v power negative 1 dv is equal to negative k times x, and then we can integrate this like natural log of v1 upon v0. That's equal to negative k times, so it goes from 0 to h, so it's going to be negative kh. So now you know k is just 1 upon h natural log of v0 upon v1. That should do it. Okay, and now let's go for finding out what the time should be. So yeah, you already got this kind of dependence, right? The dependence of velocity with time. So this will be v power negative 2. Actually, let's put that negative right there. And then dv is equal to k times dt, and then integrated this thing. So yes, negative 1 upon v squared. So 1 upon v. So 1 upon v as it goes from, I don't know, v0 to v1 is equal to, so k times whatever time required is. So the 1 upon v1 minus 1 upon v0 is equal to k. Wait, what's k? It's this thing, 1 upon h natural log of v0 upon v1 times t. And that's it. We got what the time required is. Oh, this was easy. So time required is just, yeah, h upon natural log of all that stuff. So h upon, instead just write it differently, h upon, no, okay, natural log of v0 upon v1 is better, because v0, natural log of v0 minus natural log of v1 doesn't make sense. v0 is not a pure number. Okay, and times 1 upon v1 minus 1 upon v0. Perfect. Should be 1 upon v0. Yes. Oh yeah, it does make sense. It's positive and everything. Cool. Because v1 is smaller. So 101 done. Let's go to 102. A small bar starts sliding down an inclined plane, forming an angle alpha with the horizontal. Okay, so inclined plane forms alpha with the horizontal. A small bar, by bar they just mean the mass, right? A mass starts falling down. Okay. The friction coefficient depends on the distance x covered, as k is equal to ax, where a is a constant. Oh yeah, sure. K is equal to ax. Oh, okay, so the friction coefficient. But what's x? Distance covered. Find the distance covered by the bullet till it stops. Oh, okay. So fine. First of all, don't view it like this, or maybe just view it like this. I don't know. So this will be g sine alpha acceleration in this direction, and this will be coefficient of friction times g cosine alpha in this direction. So the acceleration will be g sine alpha minus kg cosine alpha. That's our acceleration, so you can say, right? And it starts sliding down, so initially it should be 0, right? The friction coefficient depends on the distance x covered, as k is equal to ax. Oh yeah, so k changes. Oh, then it should be w over here, because you can't use two a's at the same time, meaning different things. Find the distance covered by the bar. So since we till it stops, so for that you can just do dv upon dx, right? Yes, like this will be v dv upon dx. That would make perfect sense. So then you just got v in terms of x. So yeah, so you can just integrate this thing, v squared, and it goes from, well, 0 to v. So v squared upon 2 is equal to integration of this thing. So this guy g sine alpha, this will be g sine alpha times x minus, so you got g cosine alpha, and what's k? K is ax, so integration of that thing will be ax squared upon 2. Perfect. So it's got b squared is equal to 2g sine alpha x minus g cosine alpha ax squared. Okay, and what do you need to figure out? Find the distance covered by the bar till it stops. First of all, simplify this thing. B squared is equal to, I'm gonna take g out, and let's also take x out. So it's gonna be 2 sine alpha minus a cosine alpha x. That should do it. So first of all, when will this be 0? When will b squared be 0? When that happens, either x is 0, which is, no, that's not correct. And the other thing will be, I mean, x equal to 0, it does give b equal to 0, but that's not what we're looking for. Other thing would be 2 sine alpha upon a cosine alpha. That's the other root of this equation. So, oh, you just got the thing. So the distance traveled, that will be 2 sine alpha upon a cosine alpha. Oh, isn't that just 2 tan alpha upon a? Yes. Okay, so you got the distance traveled. Now, what else do you need to do? You need to figure out the maximum velocity. Fine, so just quadratic. You know the maximum velocity is when the x value will be between the zeros. So it will be between 0 and this value. So it should just be tan alpha upon a. It's sine alpha upon a cosine alpha. So putting that in here, just get g times. So, God, what should it be? A cosine alpha. Then what here is got, well, it's just going to be sine alpha, so sine squared alpha. There we go. It's got what the distance is and what's the maximum velocity. That will be this quantity, right? So it's g sine squared alpha upon a cosine alpha. Cool. This is done. Next question. This was very easy. A body of mass, come on. Body of mass m rests on horizontal plane with friction coefficient k. At the moment t equal to 0, horizontal force is applied to it, which varies with time as this. Okay, where a is a constant. Oh, so it's just, yeah, fine. I understand this. Horizontal plane, friction is there, coefficient k. Force is in just one direction, so a is a horizontal vectorization, and then it's varying with like this. Okay, fine. What do you want to find? Find the distance traveled by the body during the first t seconds after the force action begins. Oh, okay, I see what's happening. So till some t naught, it won't move, and then after that it will start moving, right? So that's when the actual motion starts. So what's t naught? So that will be when a t naught should be equal to k mg. Yes. So t naught is just k mg upon a. After this, the actual motion will start. Yes. So what is the acceleration after that? That will be at upon m. Yes, at upon m minus the friction, which is just kmg upon m. It's like kg. But wait a second. Kg is just a upon m times. Of course, I expected this to be happening because that's when the real start is, right? So at that point it will be 0, and then it will start to increase linearly. So you could just use t1 as t naught as yeah, because yeah, like that. After that, it will actually start increasing linearly. So you can go with f is equal to a into t1 as t naught. So that f will be the net force on this. Right. In fact, you know what? Let's call t1 as t naught as, I don't know, t1. Right. And now this is our acceleration. So this is our dv upon our dt1. So the velocity will just be integration of these things like a upon 2m t1 squared, and then and what's the initial velocity? So at the real start it will be 0, and integrating this once again just got a upon 6m t1 cubed. So that's our position. And what do we need to find out? So in first t seconds, find the distance traveled. Ah, it's just this thing. Cool. And distance and displacement are the same, of course, because it's just in one direction and it's not going back or anything. This works. Yes. So it's just gonna be x is equal to sorry 81 cube upon 6m, where t sorry, and what's t1 by the way? T1 is just t minus t naught, and what's t naught? T naught is kmg on a. That should do it. Next, 104. A body of mass m is thrown this okay thrown straight up with a velocity v naught. Find the velocity v dash with which the body comes down if the air drag equals kv. Oh, okay. K is a constant, v is the velocity of the body. So, oh no, it changes with right. So whenever it's going upward, the drag is down, and when it's going down, it's up. That's complicated. If this was some kind of odd number, then we could just write I don't know, if this was kv cube, negative kv cube, that would have been it, right? Because whenever v is going down, you can go just up, and yeah, sign will change accordingly. But kv squared, come on, are you serious? This will be 2k's sorry, a 2k's problem, right? Two, yeah, fine. So while going up, what's the equation of this motion? So what's the acceleration? So the deceleration in this case, that will just be equal to kv squared upon m, and then minus, so plus g, it's adding with it, is equal to negative dv upon dt, I guess. Oh, and then when it's going down, what's the motion's equation? Oof, okay, this is x. What do we need to figure out though? Oh, velocity v dash with which it comes down. What's the same? So we will need something to link one case to other. What? The height, of course. The height will be the same. Oh, we can do this. So instead of doing this, we'll just write as v dv upon dx, because why not? And yes, so v is upwards, x is upwards. Okay, now it's coming down. What's happening? So its velocity will be negative and everything. What's this guy? What this guy's acceleration is so deceleration, that will be g minus of kv squared upon m, because now it's going down. This will be equal to negative v dv upon dx even now, right? No problem. Uh, wait, no. Wait a second. So dx is negative and v dv is, so dv is also no, it's positive. Wait, no, it's fact. Sorry, dv is also negative because the velocity is now negative in this case, right? Yeah, that's the upward acceleration, and that, of course, we can write like that. So it's correct, no problem. So now what do we do? It's got v right there or something. Uh-oh. Oh, this is bad. Fine, let's try to do something. Let's integrate this guy. So how do we do that? We'll put this over there. So it's got dx is equal to negative, or I'll just put negative dx, or negative 2 dx, even better, is equal to v2 v dv, which is basically like v squared upon, well, g plus kv squared upon m. So integration of this thing will just be natural log and all that stuff. So from here you can say negative 2. So as x goes from 0 to h, so 0 to h will be equal to, so natural log of g plus kv squared upon m, and it goes from v is equal to, oh, this is getting tight, isn't it? Oh. Now this looks better. Ah, my brain hurts. Fine. This goes from where to where? It's going from so initially v is what is it? V naught. Finally it's zero. So that will be natural log of g upon g plus k v squared upon m whatever. So it's got 2h is equal to natural log of well, 1 plus kv squared upon mg. That should do it. So that's the one equation that we need. Get rid of all of this. Just doing it. Okay, and let's go for the other equation, which was so this equation, right? So then you just got negative dx is equal to, or in fact, you know what, let's keep that negative there because maybe we'll need it sometime later. It's got dx, or let's say 2 dx is equal to negative 2v dv upon g minus kv squared upon m. Oh, I missed something, didn't I? Oh no, you had to divide by, of course, you had to divide by k upon m over here because when you integrated this thing, there was a k upon m, right? So that would be m upon k right there. Yes. Now this thing over here, we will do it correctly. So this is like d of negative v squared. So then we have to do it, yes, divide by that, m upon k, natural log of, well, this thing g minus k v squared upon m. It goes from where to where. So initially it's at 0. Finally it's at the negative v dash. So negative, keep in mind negative because it's going down. And then h goes from where, so sorry, x goes from, well, it's always positive. So it goes from capital H to 0. So it's coming negative 2h right there. What am I writing? 2 pi, negative 2h. So 2h is equal to, you can just, what is this? 2h, you can just change the sign. So, sorry, change these limits, right? So this will be m upon k, natural log of, when you put 0, it is g, and when you put negative, is that, right? So it's going to be like 1 upon all that stuff. So 1 upon g minus, well, that g is gone anyway. Just divide by that. So 1 minus k v dash, call this v1 because that's easier to write. And now what? Well, okay, you see this, k upon m, k upon m. You see that these are equal, right? So, oh, and you can write this as negative. So then their addition, of course, makes perfect sense. So this is like, yeah, we'll just clear off all of this because now it's not important. So what it's saying is that 1 plus kv squared upon mg times 1 minus kv squared, sorry, v1 squared, it's supposed to be not, that upon mg as well. Oh, it should be mg, sorry. That should be 1, not 0, 1, because natural log of this plus that, sorry, plus natural log of that is equal to 0. So, yeah, natural log of a plus natural log of b is equal to 0, so ab is equal to 1, of course. Makes sense. And now we need to figure out what v1 is, so divide by that. This is getting handful to write, so I'll just say k upon mg is equal to a. So we'll have 1 minus av1 squared is equal to 1 upon 1 plus av naught squared. And then you just got av1 squared is equal to 1 minus of 1 upon, yeah, all that stuff. That will just become what? Well, av naught squared upon 1 plus av naught squared. Oh, look, a cancels. So you can just take the square root now. v1 is equal to v naught upon square root of 1 plus av naught squared. This is perfect. So cancel all of this. So just got square, sorry. Yeah, just v1 is equal to v naught upon square root of 1 plus. So what's a, by the way? It's just this thing. Just put that in there. So 1 plus k v naught squared upon mg. That should do it. Okay, next question. 105. A particle of mass m moves in a certain plane p due to force f whose magnitude is constant. Is this figure about that? whose vector rotates in that plane with a constant angular velocity or wait, what? Oh, so F is okay. Assuming the particle to be stationary at the moment t is equal to 0. Find its velocity as a function of time and the distance between the particle between two successive stops. Oh yeah, so like initially it's at 0 and then some other time it will be at 0, I don't know. Mass m moves with certain plane p due to force F. Magnitude constant. Vector rotates in plane with constant angular velocity omega. Wait a second, what? Constant magnitude and rotation. You know what? Okay, this might be a crazy idea, but what if we use complex numbers for this? I know, I've used complex numbers everywhere. Maybe you guys would like it. But what if we do that? So we'll just have F is equal to whatever its magnitude is, or I think F naught. F is the magnitude, right? We just have that. So our acceleration, that will be so as a complex number. Isn't this weird? Yeah, it is. I know. So the thing why I'm doing it because it resembles phasors quite a lot. Yes. So it's like the force is changing like this and this and this and yeah, so on. So instead of writing these xy components of the force all of the time, I'll just combine them into e power I omega t. Yeah, and in the end, we are integrating two different equations, but we are doing it at the same time. You could do that, right? So integration of the complex exponential, it's not that bad because it's just integrating two different real functions and then putting them together. Makes sense, right? I guess so. And yeah, like there are integrals of complex numbers which you cannot just integrate normally as if you did it with real numbers. You can't do that sometimes. But the complex exponential is not one of those cases. So you can just integrate it the normal way. It works. It really does work. So what you have, just have the acceleration as f upon m. So the magnitude of the force that upon m, and then you got e power I omega t because it changes, right? Assuming the particle to be stationary at moment t is equal to 0. First of all, we'll integrate this to get the velocity. So velocity is just going to be f upon m I omega. Yes, and then e power I omega t. That should do it. Oh, and it goes from somewhere to somewhere. So plus some kind of constant, of course, for indefinite integration. Now they're saying that initially it's 0. So at equal to 0, velocity should be 0. So then you just have 0 is equal to f upon m I omega plus, oh yeah, sure. So it's just going to be minus 1 right there. Perfect. I guess that makes sense. Okay. Yeah. Now you got the velocity. And yes, just remember this thing, it actually represents two different, I mean, it's like x coordinate and y coordinate. Yeah, those things, but together, right? So when I do this thing, what I'm really doing is that I'm doing, okay, f upon m omega. This is basically just negative iota. So this is like 1 minus e power I omega t times iota. Now, whatever this will give as a real and imaginary parts, those things in xy coordinates, that would be the thing, right? So you got velocity, just integrate it once more and you will get, so yeah, you will get your, if I just leave it like that, because math will take care of it. Wait, we don't even need the position, do we? We just want the velocity as a function of time. You got it. Nice. And the distance between, well, okay, I mean, I cannot just, or maybe I can submit it like that. Who told me I could not do it like that? I can. If I want to, I will. Yeah. Perfect. I can definitely do it. So yes, I will do it like that. Okay, what was the other equation for this? Yes, the next question this, and B, you want the distance covered by the particle between two successive stops. distance covered. So the magnitude of this velocity, uh, yes, integrating over time. So first of all, what's the time required for two successive stops? So this velocity, its magnitude is not zero most of the time, right? Because this is not zero, but whenever this is zero, which will happen when omega is equal to, well, 2 pi, or yeah, that's the very next thing after zero, right? Whenever that happens, at that point, you will have another stop. So what we're doing is just want integration from 0 to 2 pi upon omega of the magnitude of this velocity times dt. That's our distance, right? So what's the magnitude of this velocity? It can't be that hard. So the magnitude of this thing, basically, right? Well, this is gonna be 1 anyway. So just got magnitude of this. It's like f upon 2, sorry, f upon m omega, and this is like square root of 1 minus cosine squared plus sine squared. Exactly. Now that will be 1. Okay, so it's like f upon m omega, and this thing is, ouch, my brain hurts. I don't know, I just didn't sleep well last night, so I might be a little slower today. 2 minus 2 cosine of omega t is. So, oh, this is the well-known thing. So it's just a, like f upon m omega times 2 sine of omega t upon 2, right? This is well-known. I don't have to explain this. So that's it. That's the, oh, it should be mod actually, because it changes positive, negative. Yeah. So what we are looking for is the integration from 0 to 2 pi upon omega of this whole thing. So f upon m omega, and then we just put 2f upon m omega, mod of sine of omega t upon 2. Hey, whatever dt, let's do it. But I'm thinking, okay, let's integrate with omega t and not this. So you could do omega squared and omega t, and then it would be 2 pi. Yeah. Cool. And in fact, why that? You can also go for omega t upon 2. So this will be 4 f upon m omega squared, and then the upon 2 over there and all stuff. Yeah, so d omega t upon 2. And then it is integration of this thing. So it goes from, well, 0 to pi. Yes, and 0 to pi, it's a mod of that. So it's going to be 2. Exactly. So it's like 8f upon m omega, and then integration, I mean, yeah, integration of modulus of sine theta from, well, 0 to pi, that will be 2. So it's 8f upon m omega squared, sorry. That should be the thing. Perfect. So now what do we have? We just got the distance covered by the particle. Yes, and also the velocity. You can just clear up everything else. Sorry. So a is its velocity is a function of time. The velocity will be given as, wait, so they didn't actually tell us what xy coordinates are, huh? Oh no. Oh no. This is bad. I mean, they gave us the force and everything, but they didn't tell us what. Uh-oh. Oh yes, like we cannot. In fact, this space will be different and whatnot. So you cannot even use like f times something. No, that's not doable. F e power I omega t, that is the force, the vector, but then that minus f. So that makes no sense. You just have to write it like that. F upon m omega into, well, just got 1 minus e power I omega t, that times iota. That's it. That's our velocity vector, right? It varies like this. Whatever the xy coordinates are. Sorry, whatever the xy axis are, however they're located, it varies like this. And b, this thing, 8f upon m omega squared. So distance traveled is just 8f upon m omega squared. That should do it. Man, I never thought about this, that maybe like complex numbers are the way to solve these kind of problems. This is just like completely obliterated the problem, right? So instead of doing two different equations, you can just do one equation. Perfect. Okay, let's go to 106 now. Yeah, we'll need more space, I guess. Yeah. A small disk A is placed on an inclined plane forming an angle alpha with the horizontal. Figure 1.27. So this figure. Okay, this is a disk on a plane forming an angle alpha with the horizontal. Oh, this plane forming alpha. And is imparted an initial velocity of v naught. Find how the velocity of the disk depends on the angle phi. If the what? Wait, you know what? Maybe this is also going to involve complex numbers because angles, right? How this depends on the angle. Maybe. If the friction coefficient k is tan alpha at the initial moment. Okay, so at the initial moment, phi naught is 5.2. Oh, first of all, just figure out what the friction should be. So just mg cosine alpha, and that times this tan alpha. So like mg sine alpha is the friction, the maximum friction that is. And because it's moving anyway, that's one of the friction itself. And it's directed opposite to the motion, of course. So to stop the relative motion, yes. And then there's this constant mg sine alpha acting on this thing. So basically, your accelerations are g sine alpha in this direction. You know what? Since it doesn't really, I mean, g sine alpha is just some arbitrary quantity, right? It could be any acceleration, and yeah, because sine alpha changes. Sine alpha is not known yet, right? They didn't give us the value. That's what I'm saying. So you just say, okay, g sine alpha, just call this in g naught. I'm just gonna define it like that. Okay, so what you're saying is that g naught is in this direction, g naught is in that direction, so like some velocity in this direction or whatever. Okay. First of all, let's flatten this out. So we'll take a top view of this. So, and since I want this angle to be with x-axis so that I can apply Euler's theorem, then what we'll do is we'll call this thing x-axis and this thing is the y-axis. Initially it was at A, so we'll say A is the origin. And at any given moment, this particle it might be going like this, velocity in this direction. So B vector, this angle is phi at that moment. So you will have velocity vector is equal to whatever the magnitude of this velocity is, which is also like variable because they didn't say that is a constant. So e power I phi b. This might be bad because if it's variable, this is probably not how it should be. Maybe decomposing it to xy components is better. No, the thing is this friction force, it changes with phi. So you know what? Yes, complex numbers are the way to go. Okay, so there's this frictional acceleration. I just, it's like I coined this term. I don't know who else uses it. Fine, which is g naught, and then you also got g naught in this direction. So the acceleration is basically like what? G naught into, well, 1 minus e power I phi t. Wait, no, it's not supposed to be t over there, just I phi. I have that bad habit of writing omega t, and that's why phi t. But this is gonna be like this. Okay, so you got the acceleration, you got the velocity. So what's dv upon dt? So you can always differentiate complex functions. That's not a problem. Integrating complex numbers is the problem most of the time, because sometimes, like if you go through a loop that is from 0 to 2 pi, your complex function might have an integral that is not 0, but then it looks like it's 0, right? Because you're not taking the path into account. So yeah, that's the problem that I ran with pretty early on. Yeah, but for like complex exponentials, no problem. You can still do it. Anyway, so what do you have? dv vector upon dt. That will be I v e power I phi and then d phi upon dt. Okay. Oh, also like velocity will change. I already said that it's variable. Sorry, it should be dv upon dt and then e power I phi over there as well. So in total, it's just e power I phi into, well, dv upon dt plus I. So okay, this is like if I take this to be the x-axis, then dv upon dt, it's in this direction, and then plus I, what was this once again? iv d phi upon dt. So iv, that is 90 degree in this direction, so from x to y, right? So that would be in this direction, so this upward acceleration, that's this. Yeah. Oh, so basically what we are seeing is that, okay, fine, fine. And then what's this acceleration? So you just have e power I phi dv upon dt plus iv d phi upon dt is equal to, come on, phi upon dt, like this. Cool. Now, you know what I'm thinking? We could just divide by e power I phi, right? And then you would have a real part and an imaginary part, and that would make perfect sense. But the problem is, does it physically mean anything? What do we do when we divide by e power I phi? I mean, it's pretty much the same thing as saying, like, just figure out how the equations would have been if this was your x-axis and this was your y-axis, and yeah, we would still have done it, right? But of course, it's changing with, so the x, y-axis are changing. So basically, you're doing the tangential and normal vector thing. Yeah. So all that's saying, the tangential and normal vector thing, what that would be saying is that dv upon dt, it's because of the tangential vector, that's just equal to negative g naught. Oh, this is this quantity over this, like negative g naught, and then you got positive g naught cosine phi, and then you got the other thing, so it's going like that, right? Yes, the normal vector stuff. And you are saying it's supposed to be v d phi upon dt. Wait, what? V omega, of course. Yeah, you remember that, right? It's v omega. That will be the other acceleration. Yeah, but like d phi upon dt, it's with what? This is weird. So what does this acceleration, that g naught sine phi, really mean? You got some component over here changing, and then you got other component over here changing. Yeah. Man, acceleration in, well, polar coordinates. That's what we are doing right now. In fact, that's not that bad because, I mean, we already got velocity in polar coordinates, all that stuff, right? So how did we do velocity in polar coordinate? It was dr upon dt. That was the radial velocity. So in this case too, it was the radial. Yeah, just carrying the terminology on to velocity as well. And another thing was the tangential velocity. That was r d theta upon dt, something like that. And d theta upon dt was just omega. So r omega. Yes. In this case, instead of r, we'll just use v. So it's v omega. Hey, it still makes sense because it's almost as if you replace the r with v vector. Ah, this makes sense. Yes. So other equation that you are seeing is that, man, I would have never figured out that this is supposed to be v omega. So the tangential acceleration would have been v omega. I would have never figured this out if it was not for this weird complex thing happening. Anyway, v omega, so like v d phi upon dt, that is equal to, so just looking from the diagram, it seems it's just well, so d phi upon dt, that's in this direction, so that means it's supposed to be negative g naught sine phi. That's nice. And what would have happened if I really did divide by e power? What does dividing, wait, all these v and these things, like velocity is a vector, right? So when you divide by e power I phi, you're basically multiplying by e power negative I phi. Oh, of course. Whatever this vector is, you are applying a matrix on this vector, the rotation matrix. Right. And yeah, so you are, oh wow, this is weird. And then whatever this vector is, so this will be a vector, and yes, you are applying the same rotation matrix on this vector, so it still works out. Yes. Of course, I mean the differential parts and everything, those come out on the front because matrices. That's how it works. So you can take that on the front because those are not in the vector itself, so they can be taken out. And then you apply the matrix on the vector. So it's pretty much the same thing as doing that. Wow. This is awesome. So you could just divide by e power I5 in that case, and that would make perfect sense in the physical world. Yes. So then we just have dv upon dt plus iv. And since I like, I like it in single equations, so we'll do that. d5 upon dt, or maybe you can not do it. Let's use two different equations because complex integration can be scary at times. Good thing is that, I mean, like, really, dv, v is just a magnitude. So yeah, that's just real differential. Yeah, differentiation of a real function, no problem. What's this? iv d5 upon dt. So v d5 upon dt is also real. Now what you just got g naught and then e power negative I5 minus 1, right? And if I want to integrate this with respect to time, of course, this makes sense. This makes quite a lot of sense actually. Yes. Okay, so this is awesome. But still, it's not actually going to give us anything nice because you can't figure out anything just yet. And what do I do? So the magnitude, we don't know how it changes with time, unfortunately. So how it changes with the angle. We don't know that, unfortunately. So you just have these two equations. That's all you have really. Okay, well, complex approach didn't do all that much. It would have been the same thing if I used the fact that v d5 upon dt is basically your tangential acceleration. Man, next time on, I'm going to use this fact a lot, I think. So yeah, instead of going with x and y every time, I'll just use this. Perfect. And oh right, figure out the geometry. Yes, you got this dt over here, can cancel this by dividing, of course. So this will be like v d5 upon, or maybe just divide it like this. So 1 upon v dv upon d5. That will be, so that, yeah, this will be like cosine phi minus 1 upon negative sine phi. Exactly. So you just got dv upon v is equal to 1 minus cosine phi upon sine phi, and then that times d phi. Yes. How about this? This is perfect, right? Yeah. This is awesome. Okay, and now we just need to integrate this. So that will give us how the velocity changes with the angle. Yeah. You know what I'm thinking? Let's multiply by s on both sides. Then, or you know how it happens. It's just s upon 1 plus c. This complete thing can be done like that. And then integration is just a piece of cake. How did I do this thing? Just multiply by s on both sides. So s squared, s, and then 1 minus c. Over here you got 1 minus c into 1 plus c. That's 1 minus c squared, s squared, right? And you can cancel this 1 minus c. So you just get 1 plus c down. So s upon 1 plus c d phi. So dv upon d v. Yes. Hey, that's all you actually needed. Wow. Yeah, really. No time dependence required in the question, right? 106. Yeah, all you just want is how the velocity depends on the angle phi, and we got it. Okay, whatever this thing is, psi, phi, whatever. And this is awesome. Even, oh god, even those g naught values got cancelled. So this whole thing, you don't even need to plug that in. So you can just get rid of this. And yeah, like time dependence, you can find that out, but the question doesn't ask to do that, so I won't. And then integrating this thing just got natural log of, well, v. So initially it's what? So initially it's at v naught. Finally it might be at v. So v upon v naught. So this is the velocity, all right? Yes, and then of course you got the actual velocity as v velocity. So this is the speed in reality. That will just be equal to v e power I phi t. Sorry, I phi, not, why do I write that t every time? Cool. Nice. And this is equal to, so integrating this thing, uh, this is going to be negative dc upon 1 plus c, so it's like negative natural log of 1 plus cosine theta as it goes from, well, pi upon 2 to whatever phi it's now. So this will be natural log of v upon v naught is equal to negative natural log of 1 plus cosine phi, and then over here it should just be 1. Nice. Oh yes, this is nice, really. So v is equal to v naught times, so actually v naught upon, because yeah, that makes sense. So v naught upon 1 plus cosine phi. So really your v vector actually changes like this: v naught upon 1 plus cosine phi, and that times e power I phi. Isn't this awesome? It really is. Yeah. Uh, so you know what velocity vector is now, but fine. That's all the question really asks. So we just submit this as answer. And from now on, I'm just going to write down complex exponentials to submit the vector. And yeah, I mean, why write all that stuff in brackets, cosine phi and like sine phi? No, just write it like this. Okay, 107. A chain of length L is placed on a smooth spherical surface of radius capital R. Have I done this once? With one of its ends fixed to the top of the sphere. Okay, no, I am not. The other question was a particle falling down from the surface. And I even forgot what the result was. But whatever. So it's a smooth spherical surface. It's fixed. One of the ends fixed at the top of the sphere. Okay, so something like this. What will be the acceleration W of each element of the chain when its upper end is released? It is assumed that the length of the chain is less than pi upon 2r. Fine, so it's like less than this complete quarter circle length. Yes. And when it will be released, what is the chain of each element? Sorry, what's the speed of, sorry, the acceleration? What am I saying? What's the acceleration of each element? So it's obvious that all of these will be accelerating in the, I mean, their angular acceleration about this central point, those were the same. So their magnitude of acceleration is the same, right? Yeah. Oh, you could just do that thing. Just figure out what the total torque is, right? Yes, yes. So, yeah, just figure out what total torque should be. And since we want to do this at any general time, wait, we just want to do what? When it is released. So not for the time when it's going down. Fine, no problem. So just need to figure out what the torque on this is. Torque on this about this point. Yeah, how do I figure that out? Take each element. So got this element right there, which makes angle, I don't know, t theta with it. This angle should be theta. Yes. What is, how do you figure out torque? Yeah, you got gravity acting down. There is normal force, you don't worry about. This is g cosine phi, sorry, cosine theta in this direction, and times this thing. So that times the mass actually, because the force is what we look for. Like it's gonna be g cosine phi. Sorry, why am I writing phi with him? Theta tm. That's the force, and that times this length, which is the radius. Okay, that's our torque. If you want to integrate this thing from theta is equal to, I don't know, it's like this thing is alpha maybe. So alpha to pi upon 2. What did this say really? Oh, so you don't know what this is. Well, we know this completely is just L, and then this completely is pi upon 2r. So this is pi upon 2r, and then, yeah, I mean, like this L, this angle should just be L upon r in radians. Then this just becomes pi upon 2 minus L upon r, whatever. We need to figure out what Tm is in terms of theta. Yes. Yeah, like alpha will just be pi by 2 minus L upon R. That should do it. So what's dm? Dm is r d theta, that's the length, that times the linear density, which is just small m, the total mass of this thing, and that upon the length. That should do it. So what we're doing is integration of, let's see, mg upon L cosine theta. You got this stuff. Oh, you also got r out actually. So you got 1r right there and 1r right there. So mgr squared upon L. So our torque, that's what we're looking for. L upon hour and pi upon 2, whatever. d theta, this is gone. Cosine theta, yes, that's all it is. So just cosine theta, d theta. So it's going to be sine theta as well from this to that. It's going to be mg r squared upon L. So think about it, sine theta is also from this to that. It's 1 and then minus sine of this stuff. So cosine of L upon R basically. Okay, nice. That will be our torque for this point. So we just want the actual acceleration. We'll divide this by the inertia, which is basically just because like all of these points are just r away from here. Yeah, this inertia is just mr squared. Oh, that's nice. That's the angular acceleration, and this times r. Yeah, should be capital R. I mean, capital R, small r, the same thing right here. So don't get confused. That is our W. So you can say, okay, W is G R upon L into 1 minus cosine of L upon R. Now maybe we can write it in a different way. Right? We can write this thing as 2gr upon L sine squared of L upon 2r. Yes, perfect. That's our W. So this is the acceleration for, so magnitude of acceleration for each point at the initial moment when it's released. 108. I mean, I really should generalize this, but then whatever. I don't think I'm ever going to look back at it because this is, yeah, this can be done on the test itself. Fine. A small body is placed on the top of a smooth sphere of radius capital R. Wait, what? Then the sphere is imparted a constant constant acceleration W naught in the horizontal direction of the, and the body begins sliding down. Hey, you remember we actually did, wait, what? It's acceleration, it's not velocity, sorry. Find the velocity of the body related to the sphere at the moment of the break-off and the angle between the vertical and radius vector drawn from the center of the sphere, the break-off point. Right. And also calculate this for W naught is equal to G. It's going a long way. Fine. Yeah, draw sphere. Oh, come on. Okay, so you got this center and then there's a body right there. This whole thing is going with W naught forward. So pseudo force W naught on this guy. We just draw the general FPD. So W naught in this direction, right? If it's making, let's say, what am I doing? Okay, if this is making, I don't know, theta angle with this, right? Come on. Then this is W naught in this direction, that's good. And then there's gravity acting on it. This angle, what will this be? Right, with this vertical, it's making theta right there. 90 minus theta is going to be theta right there, huh? Yeah. And this is horizontal, this is vertical, so it's a 9 minus theta. Got theta right there, huh? And that's why this angle should also be theta. G, yes. Yeah. So the tangential acceleration of this guy is just W naught cosine theta plus G sine theta. Okay, what do I do with it? We need to figure out the velocity of the body relative to the sphere at moment of takeoff. Uh, yeah, I just write some equations. So this is supposed to be. Oh, in fact, if you just tangential acceleration, you can say it's like dv upon dt where v is the speed, because it's always moving on. Of course. Um, okay, think about something better. Since it's all in theta, maybe omega is the better way to do it. So this is our, yeah, tangential acceleration. This thing upon r is what we're looking for. So this is equal to r times angular acceleration, just omega d omega upon d theta. Yes. So integrating this thing, it's got omega naught sine theta minus g cosine theta, and it goes from, well, 0. So initially it's 0, and finally it is I don't know, theta. That has to be equal to r omega squared upon 2, because initially it was 0. So then, oh, this is gone. Omega naught sine theta, and then when it's 0, it's going to be 1. So it's like plus g into 1 minus cosine theta. That's right. And that's equal to r omega squared upon 2. Okay, cool. Now, this is good and all. What about the radial acceleration and stuff? So there's a normal force. Yes. You can think about it as centrifugal acceleration like this happening. So it's just r omega squared is the centrifugal acceleration, just 2 times of all that stuff. You got this thing. So yeah, at the critical, I mean, whenever it breaks off, what happens is a normal is not necessary anymore, right? So yeah, over here the normal force, that's the one thing that's keeping it into that position as it moves, right? So over here normal is positive in this region, and then now in this region it's supposed to be negative so that it keeps on going, but it can't be. So over here normal should be 0. So what you have is g cosine theta, uh, theta critical, whatever, just, yeah. And then you got, I mean, this thing basically plus g, so wait a second. Yeah, what was that? You got omega naught over here, sine phi, sine theta. What am I saying? Okay, sine theta. Why did they use omega naught? I don't know. Fine. And this, oh, sorry, it should be minus. Or you can say this is equal to this plus r omega squared. This is w naught, sorry, not omega squared. Omega naught. Now that goes over here, just becomes 2 w naught sine theta plus 2g minus 2g cosine theta. That should do it. That goes over here, just get g into, well, minus 2, sorry. So this should be 3 cosine theta minus 2. Yes, that's equal to, well, 3 w naught sine theta. So wait a second. Okay, let's continue. Sorry. Yeah, what we need to figure out is, well, the velocity of the point, sorry, the velocity of the body related to sphere at the moment of takeoff. Are you serious? So you just need to figure out what omega is, right? So like r omega squared, it is 2v squared upon 2r. That works as well. Yeah, sure, but oh, come on, think about it. This is going to happen. What do I do with it? Unless you know how these are related, you can't actually do anything, can you? No, it's not possible like that. So now what do we do? Velocity of the body to sphere. So A is very hard to do. B is doable because we just want W naught is equal to G. When that happens, this is very much doable. But not like this. How can I do it like that? You can find this in terms of the angle, yes. But without that, how do I do it? Look off. Think. Velocity of body related to sphere. Come on, think. That acceleration, everything. I don't know. I don't know how to get it done. I could just use a two-part statement, that is, just write the relation between that velocity and theta. Yes. This is not going to help. This just won't help. And how I wish I could just cancel out some stuff. Wait, I can cancel out. Look at this. What was the thing once again? Sorry. Yeah, it was like G cosine theta minus, right? So the thing was G cosine theta minus W naught sine theta. So like integration of that thing that led us to this somehow. Yes, integration of this thing somehow led us to the opposite thing, and it somehow works out. Okay, this is crazy. So G cosine theta minus W naught sine theta, that's just this thing, right? That's equal to so at the break-off point, this should be equal to r omega squared, right? But you know that r omega squared upon 2, that's equal to, well, what's this? Omega naught sine, so W naught sine theta minus G cosine theta plus G. Add these, of course. It's just got 3 upon 2 r W, so omega squared is equal to G. Perfect. So yeah, I mean, right, it's just V squared upon R and everything. So in this case, it just gives us 3V squared is equal to 2 RG. That means V is equal to square root of 2 RG upon 3. Right, so A, the velocity of break-off, that will be square root of 2 RG, that upon, well, it should be 3. Okay, that's fine. And also for, yeah, we need to figure out what theta naught is for W naught is equal to G. Man, this is weird. Fine. Whenever W naught is G, you can get rid of these things directly. This becomes 3 cosine theta minus 2 is equal to 3 sine theta. So this is like 3 times of, so basically like cosine theta minus sine theta is equal to 2/3. Right, which is like, okay, square root 2 cosine of theta plus pi by 4 is equal to 2/3. So it's got 1 upon 3 square root 2 as the thing. So that's doable, I guess. Cancel all of this. This just tells us that theta plus pi upon 4, which is also just some acute angle plus pi upon 4, right? Yeah. And cosine of that is equal to a positive number. So it definitely cannot be obtuse because it won't make no sense. So it has to be acute. And in that case, it just has to be a cosine inverse of 1 upon 3 square root 2. This is weird. Wait, I do that. So it was like square root 2 over here and then it was 2 upon 3, right? When I divide by that, it's got to be square root 2 on the top, not in the denominator. Sorry, it should be square root 2 upon 3. This is weird. I mean, square root 3 upon 2, it's doable, but square root 2 upon 3, it's not. We don't know what this is, but this is how it is. Deal with it. So theta is just cosine inverse of square root of 2 upon 3 minus pi upon 4. Should we write in a different way? We can, sure. Square root 2 upon 3, this is going to be like, this is square root 2, this is 3. This has to be square root of 9 minus 2, which is 7, so square root of 7. Yeah. So sine of whatever this angle is, that is square root of 7/3. So the cosine of this complete angle, what will that be? That will just equal to this thing, that times cosine of 5/4 is like 1/3. So like 1/3 minus, sorry, plus because negative, so plus sine of whatever this angle is, which is square root 7/3, and uh, 1/square root. There we go. That should do it. Huh, this is even worse. What's this? Why is this? But yeah, that's just an alternate form, and I think maybe this is better looking than that. No, started like this. This is better looking. Yeah. So there we go. You got what theta naught should be. A is the more amazing result. B is fine, whatever. Special case. Not is equal to cosine inverse of square root 2/3 minus 5/4. Right. 109. A particle moves in a plane under the action of a force which is always perpendicular but complex numbers. That's it. Whenever I will see this kind of thing, where depending on velocity you have a force, right? Direction of the force varies. I'm just gonna do this, right? It depends on the distance to a certain point on the plane as 1/r⁴n. Okay, where n is a constant. At what value of n will the motion of the particle along the circle be steady? Huh? On the distance to a certain point on the plane as 1/r⁴n. N is a constant. Wait, oh come on. This is just so okay, either I could just go on proving that n should be 1, or just tell you that n should be 1, because we have seen many such cases where n is 1. Yeah, it's like v squared upon r. Wait, but then it's also omega squared r, so uh that's kind of different. So the force is, so it's like k upon r power n. That's what you're seeing. Okay, so if let's say x is, so x as a vector, that's just equal to r e power I theta, right? If that's the thing, then your velocity vector will just be equal to dr/dt e power I theta. I'm writing 5, but it should be theta. Like, okay, just excuse this. And then I e power I theta, and then d theta upon dt times r. So it should be r right there. That's the velocity. And then you can just go with acceleration and whatnot. So you can do acceleration as well. So it will be just a really big differential equation in terms of, yeah, in terms of r and theta and t and whatnot, right? In reality, it's like two different equations, but whatever. What's the acceleration though? The acceleration is the rate of this thing, which will be like, okay, let's just say dr/dt is r dot. So this will be r double dot e power I phi theta, you get the idea, plus I e power I theta times r dot, net rate of this thing. So I r dot e power I theta, and then you got, and let's just call this thing omega. Okay, plus the rate of this thing like I, so the rate of this, that's what I'm saying. Or in fact, let's just go with this first. So I r should be dot over here, double dot over here. Just don't. Yes, I r and e power I theta, and then you got, instead of having omega, you just need to have alpha, and then the rate of this thing. So plus, oof, that's gonna be negative over there. Oh come on, think about it. It's gonna have omega squared. So negative r e power I theta omega square. That should be. So let's just combine this to get the real part and imaginary whatever. First of all, e power I theta common. Then you got, let's see this and that. So r double dot minus r omega squared. Okay, plus iota times r dot, and this is weird. Why is there the r? Okay, it's like two r dots, and why is there no omega right there? There should be right. If I'm taking a derivative of this thing, it has to have an omega, right? I should have missed that, and then otherwise it's correct, right? Because yes, that's also correct. And then this is the most complicated one. So negative r e power I theta omega squared. Yes, it's correct. So iota, and let's see. So you got 2r dot omega. Yeah. And then minus, sorry, plus, yes, plus r alpha. That should do it. Okay, this is your acceleration. And what you're saying is that the force varies like this. So this is equal to k upon r power n. That and perpendicular to velocity. So you could say, okay, this times I e power I theta, where k is just some real number, positive, negative, we don't care. Oh, yeah, that's how it should be. Okay, so if this somehow happens, and you are saying that it will be in a steady, wait, what? And what will have L? Will the motion of the particle along the circle? Are you great? First of all, you said it's just moving under a plane, and then you say it's along a circle. Okay, if it's along a circle, r double dot is gone, and oh, come on. Are you serious? Come on, I did all of this for nothing. You're saying it's along a circle already. Okay, no problem. This is unbelievable. So, perpendicular to velocity, what kind of force? Centripetal force, come on. But wait, you can write this omega square. This is weird. And is either 1 or negative 1, because you can write as omega squared r, and also as yeah, this is problematic. Okay, so first of all, r dot is gone, so you can cancel this away, It has to be steady, so you can cancel this away as well. And then all you really get is just, okay, this is cancelled as well. So all you really get is that, oh, this should be 0 somehow. Wait, what? No, that's not correct. How can you have, no, wait. Oh, it's supposed to be perpendicular velocity, not, oh, sorry. This is not correct. Velocity is not this, it's this thing. Yeah, so it should be iota times all of this, except the negative e power I theta. Cancel that. So this will just be r dot. Well, that's gone. R dot is not there anymore. It's just going to be I r omega, and that times. But once again, just I. Oh yeah, it's going to be negative 1. Wait, what? No, that can't be. Oh, and that times this force, so which is just k upon r power n. Wait, no, you don't have to do that. It's just something that's perpendicular to velocity. It's not the velocity times this thing. That's not correct. So, okay, velocity is along, well, I e power I theta. That's the thing. All it's really saying is that it's just ki upon r power n times e power I theta. So somehow it still works out. Oh, sorry, ki times I e power I theta. And then you cancel this away. So it should be negative k upon r power n. So this cancels away completely. That's justified because there's no imaginary number right there. And then you just got what, like r omega squared is equal to k upon r power n. Now real question is, should I write this as r omega squared or is b squared upon r? They didn't give us which of these must be constant. Is omega constant or is V constant? What are you talking about? It's not such that, I mean, okay, at some particular force, it's gonna be like that, okay. Come on. I mean, you can always set up a circle. This is weird. It's got to have no answer in this way because it depends what we are trying to do. It depends on what we are trying to do, and yeah, that's how we'll set up the force, right? Depending on what radius you have, you can set up the velocity such that it will go in a circle. So it can be. This makes no sense. So once again, I'm just gonna leave this. It will be 1 upon r power n, right? If it's proportional to that, yeah. But for that, you should give me what assumptions you're making, what things you are keeping constant, because proportionality doesn't work like that. It's just in air. No, no. You need to first of all set up some of them to be constant, some of the variables to be constant. Only then can you say it's proportional to 1 upon r, all that stuff, right? This kind of question is just really not good. 110. A sleeve A can slide freely, so 1.28. This thing, okay. Slide freely along a smooth rod bent in the shape of a half circle of radius r. The system is set in rotation with a constant angular velocity omega. Okay, wait, so this complete thing is rotating, huh? Huh. Okay, vertical axis OO dash. Find the angle theta corresponding to steady. Come on. Seriously. Fine, let's do it. So, what's the so-called centrifugal force on this? It's going to be omega squared r, where r is the distance from this axis, which is basically like r sine theta. So, you just got omega squared r sine theta, right? That's this guy. There's gravity acting on it. There's normal force acting on it like this. Okay, so this thing is normal force acting on it like that, gravity acting on it, and then you got the centrifugal force acting on it. Yeah, and this angle is theta. Just draw a better figure actually. This is the small whatever this thing is, okay. This is making theta with the vertical, so like this is making theta with the vertical, right? Now you got normal force acting on it in this direction. You got this guy omega squared, so like yeah, this got r sine theta acting in this direction. And then you got gravity acting on it, which is just mg basically. Oh, it should be m omega squared. Yeah, you get the idea. Then it's, yeah, I mean that's pretty obvious that okay, first of all this angle must be theta, so you can say okay, this force plus that force, that's negative of the normal force. There we go. Tan theta is just this upon that, which is going to be omega squared r sine theta upon g. So it's got 1 upon cosine theta is this thing. So cosine theta is just g upon omega squared r. That's it. So at what angle will we get steady? Okay, at what angle will it be what? At a steady height. Yes, height. 110. Yeah, that's it. We just found it out. So cosine inverse of this quantity g upon omega squared r. This is it. I think I should stop now. It was amazing. I mean, I just figured out that you can use complex numbers freely in differential equations, not while integrating equations, but you can use them in the differential equations themselves, right? And yeah, it's just really nice. That's all I can say. So I will see you guys in the next video. Bye.